For centuries, our universe was seen as a static, unchanging stage. That ancient picture was shattered in 1929 when astronomer Edwin Hubble discovered that distant galaxies are all rushing away from us, and the farther they are, the faster they go. This was the first proof that our universe was growing. As NASA's science page on Hubble puts it, our universe was ceaselessly expanding outward, and all galaxies were moving away from one another. Crucially, this wasn't an explosion of galaxies flying through space, but the very fabric of space itself stretching. Think of dots on an inflating balloon surface. Every point recedes from every other, yet as one NASA astrophysicist explains, there is no edge to the surface of the balloon. This became the bedrock of modern cosmology. This expansion implies that 13.8 billion years ago, everything erupted from a single point in the Big Bang. And so, the official story was written. The universe is a self-contained system. The question, what is it expanding into, became meaningless because, as NASA experts state, if the universe contains everything by definition, then there can be nothing outside of it, and hence no edge, nothing for it to expand into. This is the clean, complete, and widely accepted story of our cosmos. It's a universe that is finite in age, but possibly infinite in extent, with no center and no boundary. It's a story that countless observations for nearly a century have confirmed. But it is not the whole story. Hidden in the noise of the data, in the deepest and oldest signals from the cosmos, are anomalies. Disturbing, persistent clues that just don't fit. The foundational principle of a uniform universe might just be an illusion, and the evidence that shatters it has been hiding in plain sight for over a decade. The standard model of cosmology reigned supreme for decades. It predicted that on the largest scales, apart from the uniform expansion of the universe, the motions of galaxies should be essentially random. But in 2008, a team of astronomers led by Alexander Kashlinsky at NASA's Goddard Space Flight Center decided to test this prediction. They used data from the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite designed to create a detailed map of the universe's oldest light. They weren't looking at the light itself, but at how that light was subtly distorted by massive galaxy clusters moving through space. What they found was not random at all. It was coherent, it was massive, and it was moving in a direction it shouldn't be. They discovered that a huge collection of galaxy clusters, spanning a region of space billions of light years across, was all being pulled in the same direction, toward a point somewhere between the constellations of Centaurus and Vela. This was not the expansion of the universe. This was a separate, superimposed motion, a collective drift at a staggering speed of roughly 2 million miles per hour. This massive, coordinated movement was dubbed dark flow. The discovery was so jarring that it defied all conventional explanation. The structures we can see in our observable universe, the known superclusters and great walls of galaxies, simply do not contain enough mass to exert such a powerful and widespread gravitational pull. The team checked and rechecked their data, and the signal refused to disappear. The implications were so profound that even NASA's own official press release on the findings stated the most likely and most shocking explanation. The WMAP team suggested that this unexpected motion of clusters is the gravitational attraction of matter that lies beyond the observable universe. Let that sink in. The official explanation from a NASA science team was that a significant portion of our universe is being pulled on by something we cannot see, something that exists outside the known boundaries of our reality. The observable universe, the sphere of existence we can possibly see, is currently estimated to be a bubble about 93 billion light-years in diameter. This isn't a physical wall, but a horizon of light and time. The universe has only been around for 13.8 billion years, so the light from any object farther away than that simply has not had enough time to reach us. It's the edge of our vision, but not necessarily the edge of existence. Dark flow suggested that vast structures of matter, entire universes worth of mass perhaps, lurk out there in the unseeable darkness, and their gravity is reaching across the horizon to pull on our corner of the cosmos. The discovery was, and remains, intensely controversial. It directly contradicts the cosmological principle, the idea that the universe should look the same in all directions. A massive directional flow implies a preferred direction, an asymmetry in the very fabric of space-time. It breaks the elegant symmetry of the standard model. Alexander Kashlinsky himself, in an interview with Space.com, acknowledged how unsettling his findings were. He stated, "We understand why this idea is so annoying at times. Part of the motivation was to rule it out. But it is in the data. We don't see it going away. The tidy, self-contained universe of the textbooks, the one with no edge and no outside, suddenly seemed to be leaking. There was a gravitational draft coming from under a door we weren't supposed to know existed, and scientists suspected that whatever's tugging the matter may lie beyond our observable universe. Dark flow was the first great crack in the wall of conventional cosmology. But a gravitational pull from an unseen source is one thing. What scientists found next wasn't a gentle pull, but a violent scar on the face of creation itself. If dark flow was a mysterious pull from beyond the veil, the next clue was a giant, unexplained wound in the most ancient artifact we have ever observed, the cosmic microwave background, or CMB. The CMB is the very first light of the universe, an afterglow from the Big Bang that was released when the cosmos was just 380,000 years old. It fills all of space, a faint cold radiation that serves as a baby picture of our universe. In this picture, the tiny temperature fluctuations are the seeds from which all future structure, including every star and galaxy, would eventually grow. The standard model of cosmology makes incredibly precise predictions about the size and distribution of these fluctuations. And for the most part, the observations match the predictions perfectly, except for one spot. In the direction of the constellation Eridanus, there is a patch of the CMB that is far larger and far colder than it has any right to be. It has been dubbed simply the CMB cold spot. It is a statistical improbability so extreme that the chances of it appearing randomly in a universe like ours are less than 1 in 1,000. For years, astronomers tried to explain it with conventional physics. The leading hypothesis was that the cold spot was an illusion created by an immense supervoid between us and the CMB. A supervoid is a vast region of space with far fewer galaxies than average. According to Einstein's theory of general relativity, as light from the CMB travels through such a void, it loses a tiny amount of energy, making it appear slightly colder. Scientists pointed their telescopes at that patch of sky, expecting to find a great cosmic desert, an enormous void millions of light years across. They found a void, yes, but it was nowhere near empty enough to account for the shocking coldness of the spot. The supervoid hypothesis failed. With the conventional explanation falling apart, some researchers were forced to consider a possibility that was once firmly in the realm of science fiction. A feature article in Scientific American laid out the radical new idea in stark terms. It stated, "The cold spot might be the evidence of a collision with a parallel universe." This wasn't just idle speculation. It was based on a model where our universe is just one bubble in a much larger multiverse. Researchers at Durham University modeled what would happen if our bubble universe collided with another. Such a cataclysmic event would send a shockwave through the fabric of our space-time, draining energy from the region of the collision. This would leave a permanent scar, a bruise on our cosmos, that would be visible today as an anomalously cold spot in the CMB. After their analysis, the Durham team noted that after ruling out a simple cosmic void, only this one speculative explanation seemed to fit the data. Even the scientists who proposed it admitted the scenario was extremely unlikely. Yet, it remained one of the only explanations left standing that could account for the data. Suddenly, the two greatest anomalies in modern cosmology were pointing in the same terrifying, exhilarating direction. Dark flow, an unexplained pull from beyond the horizon. The CMB cold spot is a possible scar from a cosmic impact. One is a pull, the other is a push or a bruise. These weren't just anomalies, they were invitations to a new terrifying cosmology. A cosmology where our universe isn't unique, but merely one insignificant bubble in an infinite, violent ocean. These unsettling clues demanded a new map of reality, a new story of the cosmos that could account for them. The ideas that emerged were not science fiction, but the logical, if mind-bending extensions of our most successful theories about the universe's birth. The most prominent of these ideas is known as eternal inflation. The standard Big Bang theory already includes a phase called cosmic inflation, a moment of ferocious, hyper-accelerated expansion that took place in the very first trillionth of a second. This inflationary phase was first proposed to solve some deep puzzles in cosmology, like why the universe is so geometrically flat and why distant regions of the cosmos look so similar. Inflation smooths out the universe, ironing out any wrinkles or curvature and setting the stage for the gentler expansion we see today. Eternal inflation theory proposes that this process, once started, never truly stops. While inflation ended in our pocket of space-time, allowing our universe to form, it continues unabated in the vast expanse beyond our cosmic horizon. This creates a chaotic, eternally expanding multiverse, a cosmic foam where new universes are constantly being born. Imagine an infinite ocean of boiling water. Our universe is just one bubble that has formed, expanded and cooled. But all around it, the water continues to boil, constantly creating new bubbles. Each of these pocket universes would nucleate from the inflating background, expand into its own Big Bang, and cool to form its own set of stars and galaxies. Crucially, each bubble could have its own unique laws of physics. The fundamental constants of nature, the strength of gravity, the mass of an electron, might be different in each bubble. Some bubbles might be sterile, fleeting, and dead. Others, like ours, might have just the right combination of properties to allow for the emergence of complexity and life. This isn't just a wild guess. It's a natural consequence of combining inflationary theory with quantum physics, and it provides a breathtakingly simple and powerful explanation for the anomalies we see. A Space.com article that explored this very idea notes that under inflationary multiverse thinking, some cosmologists think that our universe is actually only a bubble of space-time. Other bubbles may also have been created, and perhaps something in one of the other bubbles is tugging at our universe. In this framework, dark flow is no longer a mystery. It could be the gravitational pull from a massive neighboring bubble universe, or a whole cluster of them, their immense gravity reaching across the inflating void to tug on our local group of galaxy clusters. The CMB cold spot is also explained. It could be the literal, physical scar from a direct collision between our bubble and another one in the distant past. So when we ask what the universe is expanding into, the theory of eternal inflation gives a stunning answer. It is expanding into more multiverses. It is one bubble among countless others, each a universe in its own right, all existing within a grander, self-reproducing cosmic superstructure. The outside is not nothingness. It is an endless cosmic factory churning out new worlds. And our universe is just one of its infinite products. While the multiverse offers one possible answer, another, equally strange theory emerges from a different branch of physics: string theory. For decades, string theory has been the leading candidate for a theory of everything, an attempt to unite the two pillars of modern physics: Einstein's general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which describes the other forces and the subatomic world. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional vibrating strings of energy. But for the complex mathematics of the theory to work, it requires that the universe possess more dimensions than the three of space and one of time that we perceive. This leads to a model of the cosmos called brane cosmology. The name is derived from the word membrane. In this view, our entire three-dimensional universe is nothing more than a membrane, or brane, floating within a higher dimensional space, often referred to as the bulk. Imagine our universe is a single vast sheet of paper floating in a room. We are born on this sheet, we live on it, and we will die on it. We, and all the particles and forces we are made of, with one crucial exception, are like ink drawings, permanently stuck to the two-dimensional surface of the paper. We can move left and right, forward and backward, but we can never move up into the third dimension of the room. That one crucial exception is gravity. According to brane cosmology, gravity is not confined to our brain. It is a property of space-time itself, a curvature in the very fabric of reality. Therefore, it can leak out of our universe and into the higher dimensional bulk. It can also leak from the bulk, or from other branes floating in the bulk, onto ours. The European Organization for Nuclear Research, or CERN, explains that if these additional spatial dimensions exist, it could explain why the universe is expanding faster than expected, and also why gravity is comparatively weak. This offers a potential solution to one of the biggest mysteries in physics. Why is gravity so much weaker than the other fundamental forces? A simple refrigerator magnet can overpower the entire gravitational pull of the Earth to hold up a piece of paper. In brain theory, this is because most of gravity's strength is diluted, spread out across these extra unseen dimensions. What we feel is just a tiny fraction of its true power. Furthermore, scientists at CERN are actively searching for evidence of these extra dimensions with the Large Hadron Collider. One way they do this is by smashing particles together at incredible energies to see if some of the energy or momentum from the collision disappears. If it does, it might be evidence of gravitons, the hypothetical particles of gravity, escaping our brain and leaking into the bulk. This theory offers a different but no less profound answer to our central question. What is the universe expanding into? In brain cosmology, it might be expanding within this higher dimensional bulk. Our 3D slice of reality is pushing its way through a larger, unseen hyperspace. Some string-inspired theories even suggest that the Big Bang itself was caused by the violent collision of two of these brains, a cosmic clap of thunder that birthed our entire reality from the energy of the impact. But if our reality is confined to a membrane, it begs an even more disturbing question. Is our three-dimensional world even real to begin with? We have journeyed from a self-contained cosmos to a multiverse of bubbles and a universe floating in higher dimensions. But there is one final theory, perhaps the most abstract and philosophically challenging of all, that suggests the outside isn't a place at all, but a screen on which our entire reality is a projection. This is the holographic principle. The idea was born from the deepest paradoxes surrounding black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered something deeply strange about the information that falls into a black hole. According to quantum mechanics, information can never be truly destroyed. But according to Einstein's theory of general relativity, anything that crosses a black hole's event horizon is lost forever. This is the black hole information paradox. The key insight came when they calculated the entropy, or information content, of a black hole. They found it was not proportional to its three-dimensional volume, but to the two-dimensional area of its surface, its event horizon. It was as if all the information about every star, planet, and particle that had ever fallen into the black hole was not lost inside, but was somehow encoded on its surface. This startling result led physicists Gerard Hooft and Leonard Susskind to propose a radical extension of this idea. What if this isn't just true for black holes? What if it's true for the entire universe? The holographic principle suggests that our entire three-dimensional reality, everything we see, feel, and experience, is a projection of information encoded on a distant, two-dimensional boundary surface at the edge of the cosmos. In this view, the universe is a hologram. The universe operates on a similar, but far more fundamental principle. Our three-dimensional reality is the projected image, and the hologram itself is a two-dimensional surface at the cosmic horizon, containing all the quantum bits of information that describe our universe. In this view, outside might not be extra space, but information. The edge of the universe isn't a spatial boundary you could travel to, but an informational screen from which our physical reality emerges. This theory is wildly speculative, but it is taken seriously by many theoretical physicists because it offers a potential pathway to reconciling quantum mechanics and gravity, the holy grail of modern science. It reframes our entire understanding of reality. It suggests that at its most fundamental level, the universe is not made of matter and energy, but of information. Space and time themselves may not be fundamental, but emergent properties of this underlying quantum code. If the holographic principle is correct, then the question, what is the universe expanding into, becomes meaningless in a completely new and profound way. The expansion of our 3D universe could be the result of some complex process unfolding on that distant 2D informational screen. The outside is a different layer of reality entirely, a fundamental code that generates the holographic illusion we call our cosmos. We can't go there any more than a character in a video game can step out of the monitor and into the circuitry of the computer. We are not in the universe. We are the universe's projection of itself. And if our reality is just a projection, it means the ultimate truth of existence isn't out there in the cosmos, but written in a code we may never be able to read. We stand at a precipice of understanding, looking down into a chasm of possibilities. On one side is the safe, established ground of the standard story of cosmology, a lone, self-contained universe, expanding into nothing because there is nothing else. On the other side is a wilderness of radical, unproven, yet compelling ideas, each offering a different vision of what lies beyond. A multiverse of infinite bubble worlds born from an eternal cosmic foam, a higher dimensional bulk through which our universe floats like a single sheet of paper in a library, or a holographic projection from a screen of pure information at the edge of time. These ideas are not mere fantasies. They are the serious mathematical consequences of our best theories, born from the need to explain real, observed anomalies in the cosmos that the standard model cannot account for. The impossible motion of dark flow and the cosmic bruise of the CMB cold spot are the clues that have driven us to this intellectual frontier, but they remain, for now, beyond our ability to prove. NASA itself notes that, by its very definition, our universe is self-contained, and we have no way to test or observe any other universe, making such ideas practically untestable. This is the core of the scientific reticence. It's not a conspiracy of silence, but a disciplined commitment to evidence. To claim proof of another universe would require extraordinary evidence, and right now, all we have are tantalizing shadows. And yet, the search continues. Humanity is building a new generation of cosmic eyes. As NASA notes, upcoming missions, ESA's Euclid, NASA's Roman Space Telescope, the Vera Rubin Observatory, and the James Webb Space Telescope, will usher in a new golden age of cosmology. They will map billions of galaxies, creating 3D charts of the cosmos with unprecedented precision. Gravitational wave observatories like LISA may one day detect primordial ripples from the Big Bang itself, potentially finding a smoking gun that could confirm or deny the theory of cosmic inflation. Each new piece of data may tighten the constraints on these wild ideas, perhaps ruling some out, or, just possibly, providing the first objective evidence that one of them is true. But we must also face a humbling and challenging truth. As one astrophysicist gently explained, there isn't any edge to the universe, as in the edge of your school grounds where there is more property beyond. The only true edge we know for sure is our horizon of observability, and thanks to the discovery of dark energy, a mysterious force making up nearly 70% of the cosmos that is causing the expansion to accelerate, that horizon is becoming harder to see past. This acceleration is pushing distant galaxies away from us faster than the speed of light. As NASA points out, some parts of the universe are outside of our horizon, and since the expansion appears to be speeding up, these will never be observable to us. A cosmic curtain is closing. The search for what the universe is expanding into is a race against time. We are trying to solve the ultimate puzzle as the pieces recede from us forever. The quest straddles the line between science and philosophy, pushing our instruments, our theories, and our very minds to their absolute limits. While our new observatories will undoubtedly refine our picture of the cosmic expansion, the ultimate nature of the outside may forever dwell at the edge of human knowledge. We are explorers on the shore of a cosmic ocean, and for now, we can only stare out at the horizon, at the deepening darkness, and wonder what lies beyond.